A couple of days ago, while I was catching up with my YouTube video watching, I found this on the electronics channel from one of their live streams.
Can't be too off.
Even digital displays on analog power supplies produce less noise.
Can I ask all you guys a question here? So everybody says that for a bench power supply you need a linear power supply because it's low noise. And I would say that every laptop and computer out there, which are extremely sensitive pieces of equipment, are running off an ATX power supply or a laptop power supply, which is switch mode. And there can't be anything much more sensitive than a PC motherboard.
Yeah.
So why? Why do we need the linear one? I don't get it.
People telling you.
Oh, check the polarity.
Check the polarity.
I was guessing.
Yeah.
And I did.
I have to say I was a little bit surprised about Richard's comments regarding desktop power supplies and why computers use switch mode power supplies. Although I'm not a great expert on the subject, I think I might be able to provide a bit of an answer as to why you need a linear power supply, preferable on a bench as opposed to a switch mode power supply, and why computers are quite happy to use switch mode power supplies. This is a circuit I've actually started to build with relation to a potential upcoming video. Now what this circuit is a free running oscillator that uses an op amp for amplification. So it consists of basically a bridge which uses two capacitors and two resistors to form a high and low pass filter, and those filters are then subjected to the non-inverting input of an op amp, and then some feedback is applied, and this creates a free running oscillator which actually generates a sine wave. Whilst trying to build the free running oscillator, my first attempt, this is the output that I managed to achieve, and I felt that I was getting quite close. Unfortunately, that wasn't the case, so I continued to mess around with this circuit quite a lot and couldn't actually get it to work with the component values that I actually selected. But it wasn't until I actually powered this from a linear power supply that I realised that I was way off base. So let's just switch this over to a linear power supply right now, and then we can see the difference. Okay, we're now running from a linear power supply, and you can see that the oscillation or the output from the circuit is totally different and really doesn't bear any resemblance to when running from the switch mode power supply. So as we can see, we've got a nice stable sine wave coming out of this this oscillator, which is powered from a linear DC power supply. Let's just have a closer look at the waveform. This isn't the best scope, but so as you can see, we've got quite a nice sine wave coming out of this guy. It is a little bit on the slanted side, but you know, it's pretty good. Now let's just zoom in a little bit. Okay, so we can see there's a nice constant waveform. There's no noise on that whatsoever. It looks pretty good. So I'm now going to change to the switch mode power supply. So just bear with me for a second. Okay, so we're now running from a bench switch mode power supply, and instantly you can see that the whole thing is flickering quite a lot on the scope. And if we actually zoom in, so this isn't the best scope to see this, but if we zoom in, we can actually see all of the noise that's introduced into this circuit simply by using a switch mode power supply. This is a proper bench switch mode power supply. So Richard, that's why you need a linear power supply. I'll just change back to the linear power supply again. And that's the linear power supply. Linear power supply. Switch mode power supply. So once again, switch mode power supply, linear power supply. So when I first started in my digital electronics voyage, which was basically in the late 1970s, early 1980s, basically we had the 5V TTL logic ICs, and at that time there wasn't really that much in the way of switch mode power supplies out there, to be fair. Probably the most common switching power supply would have been found in a TV with the line output stage and the flyback transformer. As far as I'm concerned, back in the day, to overcome a lot of problem with noise, the logic levels were set in this somewhat unusual way, where you have different input and output thresholds for the ICs and different levels for logic 0 and logic 1. But if we look at this, we'll notice that they're all quite a way above ground. So by doing this, that automatically gives you a lot of noise rejection on the power supply, regardless of whether it's a good power supply or not. As we can see, as the technology has advanced, we've gone to lower and lower voltages as time has gone on. And if we take the 2.5 CMOS, for example, we can see that actually the difference between the output and the input low is actually gone up. It's gone up from 0.2 to 0.7, which is 0.5 of a volt, whereas previously in the TTL logic it was 0.4 to 0.8, which is 0.4 of a volt. And obviously when CMOS was first introduced, that was 1 volt, and etc. But we can see that as time has progressed, that although the voltages have come down, the noise floor as a percentage has actually increased. So if we stay with the old-fashioned TTL gates as an example, we can see a voltage input of 5 volts. And this little graph depicts the input and output levels. So the output signal level, so a low is considered between 0 and 5 volts, and a high 2.7 to 5 volts, and a low on the input side is 0 to 8 volts on a low and 2 to 5 on a high. So that clearly gives us a hysteresis to start with, which is a very good way of filtering out spurious signals. And then this graph then depicts the actual noise level. So this is not necessarily power supply noise, but this is noise immunity from the various elements that would be on the PCB. So your noise margin is basically the difference between your output and your input levels. We can see in this example of a typical modern clock generator circuit as opposed to an old PLL type. The PLL type has various components: a phase frequency detector, filters, voltage controlled oscillators, and then dividers in the circuit. Now all of this adds to the noise of the clock, where modern clocks are a much more modern approach where they actually look at the phase error and adjust the phase output and have correction for the clock signal to give you a much cleaner, less noisy clock. So then I've got an example of a couple of papers from semiconductor manufacturers and researchers. It's basically a paper outlining noise reduction techniques in high performance SoC integrated circuits. This paper goes into quite a lot of detail as regard to testing procedures and techniques, and then makes recommendations on various methods of reducing noise or increasing noise immunity. And I've also got a paper here from Intel with regard to the design of the Pentium 4 processor, and as we can see, this is a 12-page paper that just touches on the subject of the design processes with relation to noise immunity for the Pentium 4. Again, it's quite an in-depth paper, goes into analysis and design specifications for the CPU itself to make it as noise tolerant as possible. And the last thing I want to do is just have a look at a few pictures of some various ages of motherboard. So this is a PC XT motherboard, and we can see here that the capacitors on the board are quite small. They're probably ceramic capacitors, quite a low value. I can't actually see any values, but I would imagine these are, low value, 100 nanofarad, that kind of thing. And there's not that many of them. We've got a couple of I think we've got 1, 2, maybe 3 or 4 tantalum capacitors, maybe 5 tantalum capacitors, or maybe a few up here, and that's it. There's no inductors on the board whatsoever that I can see, and just a few decoupling capacitors, one for each chip by the look of it. And we can see this is a 10 megahertz turbo board, so this is obviously an XT clone board. So if we come to the next generation of motherboard, now this is a socket 7 motherboard that we're looking at. So it's obviously a slightly higher frequency, has the introduction of a VRM, so we can see we've got a couple of coils and capacitors related to the voltage regulator here, probably for the CPU voltage. But we can also see on this motherboard that the capacitors have grown in size. We're now into small electrolytic capacitors, and we've also got in various inductors all over the board. Now obviously these are all necessary in the design for the higher frequency of the motherboard and for noise immunity. And then this is basically the latest generation of motherboard. I think this is an Intel 13th gen compatible motherboards, Chinese manufacturer. Obviously we've got the VRMs here now, so obviously there's a heck of a lot of filtering on the VRMs themselves, but we've also got much larger electrolytic capacitors all over this board, plus the design of the motherboard itself. The layout of all the tracks would be much more considered with regard to noise immunity. In my opinion, it's generally fine to use a switch mode power supply on an electronics workbench, but there are specific reasons and circumstances where you definitely need to have a linear power supply available, and therefore if you only have one, then it would really have to be a linear power supply for a bench, just because of the circumstance that I've demonstrated here, and there's lots of others. And then with regard to modern computers using switch mode power supplies, I tried to demonstrate that fundamentally digital circuits have always been designed with noise immunity in mind, and that started with the earliest TTL logic chips, which actually created a lot of noise themselves by using using a range of input and output voltages and hysteresis, etc. PC motherboards have had slowly increasing capacitance added onto the motherboards to help with noise suppression and filtering and bypassing the XT motherboard had quite low value capacitors added, and those capacitors have just got larger and larger and more filtering as time has progressed to enable these things to run from noisy switch mode power supplies. As I said, I'm not a huge expert on this subject. These are just my opinions. I'm sure there'll be a lot of people that disagree or have comments to make. So I hope you enjoyed this one. If you enjoyed this video, please subscribe to the channel. It's much appreciated.